So DAA, right? DAA. Okay. This is TOC, right? So I'll just start with TOC. Let me just put the syllabus sheet in front of me so that I don't tell more, so that I don't come with more. No, I don't have the syllabus sheet with me. I'm just looking at the mail which sir sent. So 1 minute. So no questions will be asked about NFAs, PDAs, or constructing Turing machines for language recognition. So you won't get questions like this. You won't get questions like construct a machine that recognizes all right. You won't get questions like this. So no questions about NFAs, PDAs, or constructing Turing machines. Fine. So no construct questions. Okay. Anyways, so TOC. But we'll just go through that because later they're like you're expected to have a clear understanding of Turing machines. So you're supposed to know what a Turing machine is, Turing machine is, but you just won't be asked to like construct them. That's it. So essentially, you're supposed to know what they are, but they won't ask you to construct any machine. Fine. So we'll just go through everything. We'll just go through everything because later I can't assume that all of you have a clear understanding of uh, what DFA, PDA, or what any of these means. Not that they will ask you about it, but when we are discussing about Turing machines, we will be using these words very lightly, like DFA and let me see. What are the other things? Uh, yes, so we'll be using those words very lightly, like DFA and a machine in general. So, in order to reach that stage, we will just go through everything. So that will we'll be familiar with all these terminologies. We can't directly skip to Turing machines, right? So, okay, fine. I'm starting now. TOC. What is TOC? Some people were asking me what is TOC? Theory of computation. Nice. Uh, Deterministic finite state automaton. Okay, very beautiful name. What is this? It is just some mathematical object which is represented using a tuple of 5 elements. Capital Q is it's written here, set of states. You have set of input characters. You have start state. You have transition function. You have transition function and capital F is you know what is a set. You also know what is a function. So just these 5 things I'm taking and putting them in a tuple, and I'm calling this a machine. What kind of a machine is this? Deterministic finite state automaton. Nice. Uh, is there anything else that is supposed to be explained here? I don't think so. Uh, this Q naught, which is the start state, it must belong to the set of states because you can't have the start state has to be a part of the set of states. It can't come from some other set. So that is one condition. Set of final states must be a subset of the set of states, which is understandable. It is very much obvious. You can't have essentially no like if you're using any state in this machine, it should belong to capital Q. It can't come from outside. So this makes sense. And delta is a function that takes 2 inputs. The one is a state, the current state in which the machine is, and the second input is the input character. So the function delta will take a state and an input character, and the output that it's going to give is a state again. But what state is it? What is the output now? The state into which the machine is supposed to go into. So input is the current state and the input letter it's reading. The output is the next state. What is the next state of the machine? So this transition function will take care of that. It will keep reading uh, the input and giving out output. Giving out output in the sense it changes the state in which the machine is currently. And size of capital Q must be less than infinity. It means it's finite. You have finite number of states. So why is it called deterministic? Because for every pair of input in the sense I'm calling it pair because you have two inputs, right? One is the current state of the machine and the other is the input letter that you're reading. So for every pair of input, you have a fixed output. That's why it's called deterministic. For example, if today is Monday, tomorrow has to be Tuesday. That is fixed. It can't be like if today is Monday, tomorrow will be either Sunday or Saturday. That's not the case. Deterministic is you know what is the output. If today is Monday, tomorrow has to be Tuesday. That is deterministic. Non-deterministic is the opposite. Like for example, if you toss a coin, let's say you get tails. If you toss it again, you wouldn't know if it's going to be tails or heads the next time. So that you can't determine what is it going to be. So that is non-deterministic. Anyway, so nice. DFA, basic understanding. Example, you can go through it. It's just basic. There's just an example. But they won't ask you to construct any of this. So you don't have to worry. So we'll just go through this. Fine. This machine recognizes all odd binary strings. Okay, fine. Let us just go through one example, but I'm telling you again, they won't ask you to make any of this. So, to just get a basic understanding, I'm going through this example. That's it. So, you have a start state. How do you know it is a start state? You basically have an arrow coming from somewhere. So, that means uh, the and all the states are represented using circles. So, you have circles here. So, the arrow which uh, the state towards which the arrow is pointing, that is the start state. And then you have other arrows in between. From state to state, you have arrows. So, and beside each arrow, you have some symbols, right? So, those are your input characters. And if you see two circles, it means that is the final state. You can have multiple final states. That's why it's a set of final states. This is just an example. So if you want to define it using the five tuple in the sense you have a tuple of five elements. That's it. That's why it's called a five tuple. So how many states do we have in total? We have two states. One is the zero state. The other is the one state. Okay, getting messages. Okay, after capital Q, what do we have? We have sigma, right? Sigma is the set of all input characters. What are the input characters here? We kind of like we're dealing with binary strings. So in this example, so 0 and 1, those are the only two input symbols this machine will ever read. It won't read anything else. What is the start state? Here we're defining the start state to be the 0, the word 0. And in the set of final states, you only have one element, so you have a singleton set. It's a set, so you have to write it as a set. I mean, they won't ask you to construct, but we're just going through an example. And what is our delta here? Delta will take two elements as input, right? One is the state. The first input it's going to take is a state. So the word 0, the word 1. And the second input that it's going to take is the is an input character. So it could either be a 0 or 1. So this means if the current state is 0 and if it reads if the current state is 0 and if it reads the input symbol input character 0, then this is the state the machine is supposed to go into. So you have a table, that's it. So this is a mapping. You're mapping a pair. What kind of a pair? We're mapping state comma input character to some states. So fine. That is what delta essentially does, right? Or do, whatever you call it. In our class, sir has been calling it delta delta. I would call it a do, but I'll just get on with the word delta. So what does this machine do? This machine recognizes all odd binary strings. Nice. For example, what do you mean odd? Uh, how do you say a binary string is odd if it ends with a 1, right? Yes. So what does this do? If you input 1, 1, what will happen? Start state is 0. If it reads a 1, it will go to 1 state. And since it's in the 1 state, if it reads a 1 again, it will go to the 1 state. So final state is 1. Nice. So if I input 1, 0, what is going to happen? If I input 1, 0, start state is 0, and then it reads the input 1. So 0, 1, you go to 1. So currently you're in the 1 state. Now if you read a 0, currently you're in 1 state, no? So in 1 state, if you read a 0, you will go to the 0th state. Now there is no more input left. So what happens when no more input is left? Now you have to check if you're in the final state or not. You're currently in the 0th state, and 0th state is not the final state. So it means the machine simply rejects the input. So here you have the concept of accepting and rejecting. After reading the entire input, if the DFA finds itself in the final state, or if it finds itself in any one of the final states, then it means the input string is accepted, or else it is rejected. So in DFA, you have this property. It's like the input string is either accepted or rejected. And when do you know if it's accepted or rejected? Until you read the entire input. Until you read the entire input, you're supposed to wait. Only then you will get to know. Okay, this is accepted or this is rejected. Like right after reading the entire input, you will know whether the string is accepted or rejected. That is how DFAs are, because we've just seen through this example. And yes, so if I change the final state now, if I remove the final state from 1, and if I just put it at 0, then my machine changes, right? So in that case, it becomes a different machine. What does that machine do? That machine would then recognize all even binary strings, because the final state is at 0. What do I mean by final state it as 0? It means it keeps reading the input characters, and because I have to check the last character, right? So this machine keeps updating its state as and when it reads new characters. Since it does this, by the time it reaches the last character, it will update its state accordingly. So if the last character is 0, then the machine will go to the 0 state. If the last character is 1, it will go to the 1 state finally. And that is what we want, right? Finally, we want this machine to tell if the binary string is odd or even. So here we are the masterminds. We are designing the machine, but in the exam, they won't ask you to design the machine. So fine, we're just going through an example. So input is accepted when the machine reaches the final state after having, yes. So you have to read the complete input, then you will know whether the input is accepted or rejected. So these kind of questions won't come. Construct a machine that recognizes all by, no, these kind of questions won't come. But you're supposed to have a basic idea, because now we'll be going to Turing machines, right? Later on. So language, I wrote something here at the top. Language or problems are equivalent. Uh, we'll see. There's an example later on. We'll just go there. And there was some discussion about grammars as well, but I did not write anything about it because it was not discussed in detail. So I just kept dot dot dot. Will not get into grammars. So you can see how machines work. Nice. So we're still dealing with DFAs, deterministic finite automatons. Is that what it is? Did I miss anything? Deterministic finite state automatons. Fine. Okay. Something we have. Say M is a machine. So right now, what are the machines that we know about? We only know about DFAs. So let's suppose, okay, fine, M can be any machine. As of now, we know that DFA is one kind of a machine. Are there more kinds of machines? Yes, there are. We'll see what they are. So language of M. Now this is new terminology. We're introducing something called language of M. So language of M represented as a L of M. So L of M is basically set of all strings over sigma that M accepts. We've just seen what does accepting mean, right? A machine accepts a string if it reaches the final state upon reading the entire input. So that is acceptance. After reading the entire input, if the machine doesn't find itself in the final state, it means the machine is in. It means the machine rejects the string. So if I take all possible input strings which are accepted by a machine and put them in one place, that set of strings is called language of M. So it means basically this machine understands all these strings. It doesn't understand anything else. Or it accepts all these strings. It doesn't accept any other string. So M accepts strings from language of M, that is by definition, and rejects all the strings from the complement of language of M. What is the complement of language of M? It is the set of all other strings that are not accepted, and not accepted in DFA means rejected. So the set of all rejected strings will fall in the complement of the language of M. Here I wrote something sigma star. We've seen what is not we've seen, but if you've paid attention to in class, sigma star is basically the set of all possible strings over sigma. So for example, if sigma is 0 comma 1, sigma star will be set of all possible strings over sigma. That would mean it is either null or null comma 0 comma 1 comma 0 0 comma 0 1 comma 1 0 1 1 0 0 0 0 0 1 0, like all possible strings using 0 and 1. The length doesn't matter. So you'll have strings of length 0, strings of length 1, strings of length 2, strings of length 3, 4, 5, 6. It goes on. So it is a very big set. So sigma star is the set of all possible strings over sigma. In the sense, you have to use the characters from sigma and start making strings. Collect all those strings and throw them in sigma star. That's it. So here I wrote something. Sigma star is equal to the disjoint union of language and its complement. So what does this mean? This means that if machine accepts all the strings belonging to its language, it means it rejects all other strings which are not belonging to the language, right? So what could those rejected strings mean? What could those rejected strings be? They're nothing but all the other possible strings that are in existence. So if see how do I? It's simple. See, I have sigma star is the set of all possible strings, and L is that small set. L is a very small set. What does L contain? L contains all the strings accepted by M. If you remove L from sigma star, what will remain? You will remain with this one L complement. You will remain what will remain? The strings that are not accepted by M will remain if you remove L from sigma star. So that is the meaning. That's it. There is nothing in this. You're taking a disjoint union because no element is common between language and language complement. So that's why this is there. That's it. There is nothing much in this. Fine. What is computation? Okay, we'll see what is computation. You have a machine, a 5-tuple, fine. A DFA in particular, but machine could be any other machine, but we'll just see. You have a machine here. Input smallest belongs to sigma star. So input is a string. So when we are dealing with machines, input is usually a string. So input belongs to sigma star because sigma star is a set of all possible strings. The alphabet is sigma. So if alphabet is like English has an alphabet, English has A, B, C, D till J. You have 26 letters in the alphabet. Now, whatever I'm speaking, they're all words, right? So they're formed by using the characters from the alphabet. So similarly, you have small s. Small s is like a word. It's like a collection of characters. That's it. So s is a string essentially. Okay, now we wrote down the characters as well. The characters are S1, S2, S3, so on until Sk. So this is a k-sized string, and every character comes from the alphabet sigma. Nice. So I'm using delta now. See, delta is the main thing. Delta changes the state of the function, right? It read, delta will take an input, and then as an output, it changes the state of the function. So delta. So computation is basically this one. Uh, you just keep reading the input and then keep changing the state of the machine. That is essentially computation. So what is happening here? Delta reads two things. Uh, what does it say? It will check the current state of the machine, and then it will read the input. So what is the input? Input is some character. It keeps reading, right? So for example, let's say the machine read S1, S2, S3, so on. S minus I also it read. Now currently it's reading Si. And while it's reading Si, the machine is currently at the state Qi minus 1. So now delta will do something. Delta will check this current state Qi minus 1. It will read the incoming input character, which is Si. And then as an output, it will give one more state by definition, because state is the output, right? So by definition, it will give an output qi. What is this qi? This qi should what is this qi? This qi is the next state. So the machine will now go into qi after reading this input. So this happens for the entire string. So for I equal to 1, 2, 3, 4, 5 till k. So this process happens while reading every single character from small s. So this is computation. You keep reading the input and then you keep changing the states of the machine. That is basically computation. So finally, the final state, if you notice, final state is going to be what? QK will be the final state, right? So initially you were at Q naught. After reading the first character, you went to Q1. After reading the second character, you went to Q2, and so on. After reading the kth character, you went to state QK. So if QK is one of the final states, how do you say that? If QK belongs to capital F, that means the machine, whatever you have, which is capital M, machine accepts small s, or else it doesn't accept small s. So this procedure is essentially computation. That's it. Uh, okay, new terminology. A language is regular if there exists a DFA M such that language of M is. So basically, languages of DFAs are regular languages. That's it. Uh, okay, terminologies are fine. Can the union of two regular languages be? I mean, they're just examples. Uh, the answer is yes. The answer is yes. It's a rough idea. It's just an example. You can go through it. I'll just so that was DFA. DFA is fine, and I gave you a hint as to what an NFA could be. Right now, so in simple words, it's like it's DFA only, but then it's no the D is not there anymore. It's not deterministic. For a given input, you can have multiple possible outputs. So how do you represent that mathematically? You just represent it like this. So if you read a state, which is if you read the current state of the machine, and if you read a character from the string, from the input string, the output will now be a set of possible states. So how do I represent a set of possible states? It is basically a subset of capital Q, right? So where can I get a subset of capital Q from? You can get a subset of capital Q from the power set of Q. So that is why you have power set of Q here. So this is how you mathematically represent the transition function of an NFA. This is in short form NFA. NFA is a short form for this. So why do you have this? It's like input will come from capital Q and sigma. So basically you will get one state and an input character. Output will be an element in the power set. What is an element in the power set? They're basically subsets of capital Q. Why do you have subsets of capital Q? It's because this is non-deterministic. For every pair for every input pair, essentially for every state comma input character, you get a set of states again as output. So it could, let's say you're in state q1 and you read character s2. Now, what will the output be? If it's a DFA, you will get one state as output. But since this is an NFA, you'll get multiple states. So you'll get a set of outputs. It could be like Q1, comma, no, not Q1. You are in already Q1, right? So Q2, comma, Q3, comma, Q4. So that could be your answer. So after reading Q1, comma, S2, you could go to either Q2, Q3, or Q4. So you have options there. Options in the sense this machine is not going to choose one of them. So here you have two things. Here the machine splits. So this is one idea. The idea is that the machine splits into multiple branches. So that is the idea. So in my example, when I said q1 comma s2 is the input and the output is q2, q3, q4. So this means in this example, the machine splits into three branches and continues with computation. We've seen what is computation, right? Computation is basically the transition function reading the input and then giving out an output. So for a non-deterministic function, for a non-deterministic, what is this? For an NFA, essentially, you will have multiple branches. So it's like, see, you've seen Marvel movies, right? You'll have timelines there. You split the timeline, something like this, something of the same kind. So this machine splits into branches, and then it's like you have multiple machines now. They're performing it simultaneously. You can think of it that way. So you won't have questions like construct a machine that does this, that does that. But you can look at the example so that you get an understanding as to what is an NFA. But mind you, they won't ask you any questions, so you can pay less attention. As long as you're going to understand the other topics, Turing machines and so on, you don't have to pay much attention here. In case you have a slight confusion, you can come back to these. So I won't be spending much time here. Uh, so there was this small discussion that we had. So since now that we know DFAs and NFAs, the question is NFA more powerful or is DFA more powerful or are they equivalent? Powerful in the sense in terms of the set of problems that they're able to solve. If NFAs and DFAs are able to solve the same set of problems, then I will call them that they're equivalent or they're equally powerful. It's not about how fast they solve the problems, it's about whether they're able to solve the problem or not in the first place. We're not talking about the speed here, we're only talking about their power, uh, their problem solving power. Are they able to solve the problem or not, irrespective of the time that NFAs or DFAs take, irrespective of the time taken? So the answer, I'll tell the answer. The answer is yes, NFAs and DFAs are equivalent in the sense they solve the same set of problems. Despite our intuition trying to tell that NFAs look more powerful because they split into multiple, no, it's fine. You can show mathematically that both of them are equivalent. So that is the essence here. What basically happened here is we are trying to represent NFA as a DFA and DFA as an NFA. So mathematically, we're able to show how they're, yes, so I've written it here. DFA and NFA are equivalent in terms of solving power. So when I said that NFA is split into multiple branches, and I told that they will simultaneously computation happens in each of those branches, right? If that is the case, then okay, let me just draw something. So how do DFAs look like? DFAs will be like, if you're in this state, then you will go to this state, then you'll go to this state. Finally, you'll reach some state. So it will be linear. This is how DFAs look like. But NFAs, what you'll have is you have some state. After reading some input, this will split into branches, and then it could go on. See, it depends on each branch. So it keeps splitting into it simultaneously keeps splitting into multiple branches. That is, you can represent NFAs like this. So this is how NFAs function. Mathematically, we can show that both of them are equivalent in terms of solving the same set of problems. If you think, if in case now, if we start talking about the time, if we start talking about the time, what I'm saying is, if when they split into branches, if the computation happens simultaneously, if it happens simultaneously, then it's fine. The time complexity will be in terms of its height. But in case it doesn't happen simultaneously, if you have to do it linearly, for example, linearly in the sense, if you have to like go one by one, this is BFS, right? BFS is, it's like this. So one by one you have to go, or else you could do DFS as well. So because this is essentially a tree, right? I can do DFS, BFS. So if I have to do it consecutively, not consecutively, what do you say? Sequentially, if I have to sequentially go through these states, then that is a problem, because sequentially, if you're going through this, it means the time complexity will now be exponential, because there are exponentially many nodes in a tree, right? But that wouldn't have been a problem if these branches, if the computation happens simultaneously in each of these branches. So that is what I wrote here. So NFAs and DFAs essentially solve the same set of problems. So they're equivalent. So we'll not look at time. If you bring time into picture, then if the branches are simultaneously, if the computation happens simultaneously there, it's fine. Same time complexity. But if you're sequentially processing them, then DFAs are better, because NFAs will take more time. Okay, now foreshadowing. Now we have something called P and NP. This is important because this will this comes under can problems be classified based on their time complexity. So you have to understand what is P and NP. So what is P? P is the set of all problems. Okay, first of all, what is a problem? I told you before, language and problem are equivalent. So they are the same thing essentially. There was an example. I think the example will come later. The example will come later. Uh, like in that example, I kind of showed like for this question, what is the problem and what is the language. So I'll come there. So for now, keep in mind languages and problems are one and the same thing. Uh, Okay, we'll come to that example later, but okay, fine. So P is a set of problems. What kind of problems? So P is a set of all problems solved in polynomial time using deterministic Turing machine. We haven't seen what we haven't gone through what a Turing machine is, so we'll come to that. So, what is NP? Does NP mean a set of all problems solved in non-polynomial time? No, that is not the answer. It's not non-polynomial. It's not non-polynomial. It is the set of all problems solved in polynomial time complexity only, but using non-deterministic Turing machine. So the n in NP comes from non-deterministic. It does not come from non or not polynomial. So both of them are polynomial time solvable problems only. It's just that P uses deterministic Turing machine and NP uses non-deterministic Turing machine. We've seen that DFAs and NFAs are equivalent. So does it mean deterministic Turing machines and non-deterministic Turing machines are equivalent as well? We'll come to that. This is, I think, the last question that we'll be going through in the notes, I suppose. As far as I remember, at the end of this TOC in my notes, that question will be answered whether deterministic Turing machines and non-deterministic Turing machines are they equivalent or not. We'll come to that. So, okay, we have an idea as to what P and NP are, but we did not go through what Turing machines are. And I told you I will show you an example, right? As to how languages and problems are one and the same. We'll see. Pumping lemma. I wonder if they will ask you to use pumping lemma. because no questions will be asked about NFAs, PDAs, or constructing Turing machines. So pumping lemma. I don't. Okay, let me see. I don't think. I don't think I don't think there'll be any question on pumping lemma because they're like you're expected to have a. We didn't even read Turing machine. So this pumping lemma is for regular languages. So since they told no questions will be asked, so you don't have to go through pumping lemma. As far as my intuition says, I don't think there'll be any question about pumping lemma. So, okay, essentially, why did some pumping lemma come into picture? It's like they're trying to show that some language is not regular. And by regular, I mean regular is a language is regular if it is a language of a DFA, right? So they're just showing that some languages exist that are not regular. So this is just one example. So okay, fine. There is some language that is not regular. So does it fall under any other language? Probably, but we'll see. Okay, yes. So here is the example that I was talking about. How is language and problem equivalent? So if you look at this example, I wrote design a machine that you won't get these kinds of questions. I'm just focusing on the example here. Design a machine that accepts all binary strings that have. Okay, so this is a this is a non this is an NFA, right? Because if you notice, if you're in the start state and if you read the input symbol 1, you have two possible states. One is the start state itself and the other is the next state. So that is only possible if you're using NFAs. In DFA this is not possible because in DFA if you have a state and an input character, you will only get one state as an output, but in this case you're getting two states as an output. That would mean that this is an NFA. Fine. The thing that I want you to look at is what, okay, in this case, what is the language? So in this case, the language is set of all binary strings with 101 or 11 as substrings. Fine. That is the language in this example. What is the problem in this example? The problem is, does the given string have 101 or 11 as a substring? So this machine answers this problem. How does it answer the problem? If it finds itself in the final state after reading the entire input. So essentially, if the machine accepts the input string, it means the answer is yes to the problem. If the machine rejects the input, which means it after reading the input it did not find itself in the final state, that means the answer to the problem is no. So the machine answers this question, yes or no. And if you think about it in the other way, the machine accepts some strings and it doesn't accept some other set of strings. So in this sense, language and problem are equivalent. So in this case, the language is set of all binary strings with 101 or 11 as substrings. And the problem that this machine is trying to answer is does the given string have 101 or 11 as a substring? So essentially, languages and problems are the same thing. They correspond to the same thing. It's the same thing essentially. So okay, fine. Uh, uh, Maybe interested people could go through this, but I don't think you'll have to spend any time here because how did pumping lemma come into existence? It's some logic is there. You can skip it. You don't have to. Uh, I mean, this was discussed in class, but then there were like no questions. Since no questions will be asked, so no explanation will be given. As simple as that. No questions will be asked, no explanation will be given. Okay, so these kind of questions won't be coming. Okay, so this is if you remember, not that you remember or something, but we discussed, at least in our class, we discussed some question about It was a question in string algorithms. We were like we had a naive method, and I think after that we used Rabin Kapp's algorithm to check if a pattern exists in a given text. So we kind of constructed a DFA for that. Uh, but they're like no questions will be asked about NFAs, PDAs. But they didn't say they won't ask about DFAs. Interesting. This even came in our lab. I don't know about your lab. Like they asked us to program this. I mean, they only said they won't ask you about NFAs or PDAs. It doesn't mean they won't ask you about DFAs, right? So okay, fine. So I'll go through this because they only said they won't ask you about NFAs and PDAs. It doesn't mean they won't ask you about DFAs. And this question is only related to DFA. So I will go through this. So it's good that we went through the DFA. Okay. So they said they won't ask questions about NFAs, PDAs, or constructing Turing machines. It does. So it wouldn't that mean they could ask you to construct a DFA? So let me just go back to DFA and see if because and wouldn't that mean I have to go through the pumping lemma of regular languages? Okay, so let me go back to DFAs. But there is nothing much complicated in DFAs as well, right? Because it's simple. You don't have big things in DFA as well. Fine. I mean, this is simple to make. So maybe just go through DFAs at least because they didn't say they won't ask questions about DFAs, no? So at least DFA part we'll go through it. There are like no questions about NFAs, PDs. Fine. Okay, so I will explain this also. Can the union of two regular languages be a regular language over sigma? So essentially, what we're doing is, let's say machine one and machine two exist. So what is happening there? Uh, Machine one will either accept a string or not accept a string, and machine two will also do the same thing. It will accept the strings of its language, or else it will reject the string. So nice. So what do I mean by union of two regular languages? It means I should find some other machine that accepts any string coming from the union of two regular languages. In the sense, let's say I have machine 1 and machine 2. So they're both DFAs. So essentially, I can say that both of them have their own languages. So L of M1 and L of M2. So what I'm trying to find out is whether the union of L of M1 and L of M2 is also a regular language. In the sense, I have to find one machine that accepts the union of L of M1 and L of M2. So the rough idea is this one. So you give the string to M1, it will read, it will either accept or reject. If it accepts, we are good to go. If it rejects, now give the same string to M2. Now M2 will either accept or reject. So essentially, if you construct this machine using M1 and M2, now this is one new machine. So from outside, how does it look like? If you give the string, the machine is either accepted or rejected. When is it accepted? When it is either accepted by M1 or M2. When is it rejected? When it is rejected by both the machines. So this is the rough idea. So this is essentially how you could make a machine that recognizes the union of two regular languages. If you can make a machine, so that means the union of two regular languages is also regular. So that is how this question is answered. Uh, okay, NFAs. And one more thing, like, not that they will ask you questions about NFAs. When I said that NFAs branch into, like, NFAs split into multiple branches, right? So what happens when and okay, fine. One more thing. I wrote this epsilon here, right? So sigma is different, sigma epsilon is different. Sigma epsilon means now, along with the usual set of characters, you also have the epsilon character. And the epsilon character is the like how you have the phi symbol in null set. Like null set is represented by a phi, right? It means nothing, so null set. Similarly, there is some, it's like the null character. So null character is essentially uh, epsilon. So empty string, null character, whatever, epsilon. So sigma epsilon will also contain the null character epsilon. So that is an addition. This will come in Turing machines as well. Sigma epsilon, not sigma. You'll get something else. We'll see. Tau epsilon, I think. We'll see. Okay, what I was telling in NFAs, uh, when it splits into multiple branches. Okay, and okay, fine. What is the significance? What do I mean by empty string? So it means there could be a possibility where the input is current state, comma, uh, null character. So, what does it mean when you read null character as an input? It means now I can change the state of my machine without reading any input character. That is the meaning. So, for example, if you're in state Q1 and you read null character, so Q1 comma epsilon, so delta of Q1 comma epsilon becomes, let's say, Q2. So, what does this mean? It means the machine changes its state from Q1 to Q2 after reading epsilon. So reading null character is essentially reading nothing. So it read no input, but then it changed its state. So that is the significance of the null character, epsilon. Okay, coming back. So why was I talking about epsilon? When I said that NFA is split into multiple branches, what is going to happen when it doesn't read, it doesn't get an input character, but then it's in some state. For example, uh, let's say this is an NFA, right? Let's say you're in the final state. When you're in the final state, it doesn't mean the process ended, right? You could still get input characters. So let's say you're in the final state and then you get the character one. Well, what do you do now? I mean, it's not defined, right? It's like if you read it, you don't do anything. In the sense, what is going to happen there? If it is not defined, it means that branch dies. In NFAs, it's like if there is nothing defined, if you get an input and if it is not defined what you're supposed to do with the input, then the computation stops over there. The branch will die, the branch will not continue. So in NFAs, that is the meaning. Uh, and okay, here we didn't use sigma. Um, I mean, we didn't use epsilon. We'll see. I think there'll be other examples where epsilon is used. But for example, if epsilon is somewhere, it means without having to read any input, you can do transitions. But uh, if the transition itself is not defined, then that branch dies in an NFA. Okay, one more thing. When does an NFA accept a string? DFA accepts the string if it finds itself in the final state after reading the entire input. When does an NFA accept a string? Uh, so NFA splits into multiple branches. You have multiple branches. So after reading the input, if like if there's at least like if there's at least one if the machine, if in any of the branches, if the machine stops finds itself in one of the final states, then that means NFA accepts the string. So for example, if after splitting into all these branches, let's say this is in the final state. That means the machine accept this. This is the accepting branch in that sense. That means the machine accepts the string, irrespective of whether the irrespective of whether in the other branches the machines find themselves in any of the final states. If there exists at least one branch in which the machine finds itself in the final state, that means in that case NFA accepts the string. Okay, fine. So we'll have to wait for the example where epsilon appears. Uh, like that example will probably be nice. Okay, we'll go through pumping lemma as well, because they didn't say they won't ask questions about. They didn't say they won't ask questions about DFAs, no. And this pumping lemma is for DFAs, so we'll just see. Let A be a regular language. There exists a number, let's say small p, and it is called the pumping length for any string. So where what is a string? String is your input string, right? And where does it come from? It comes from sigma star. If it comes from outside sigma star, that's a problem, because your machine can only read strings that are made uh, using the characters from the alphabet sigma. And sigma star is essentially that. Sigma star is the set of all possible strings over sigma. Okay, so there exists a number small p for any string of length at least p, such that we can divide S into three parts, x, y, z, so that the following three conditions are satisfied. So x, y power I, z belongs to A. So what does this mean? It means x, z, x, y, z, x, y, y, z, x, y, 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 z, and so on also belong to the language A. Interesting. And then mod y has to be greater than 0, okay, and then mod xy has to be less than or equal to p. So it's basically stating that you can divide S in such a way that these three conditions are satisfied. We don't have to go through the proof. Proof is in the next page, but you don't have to go through that. If you want, you can go through that if you want clear understanding as to why this pumping lemma is true. So this is just a pumping lemma. This is true for regular languages. Using this lemma, they try to show that this given A is not a regular language. So what is in this A? In this A, we have a null set, null string basically, because uh, when n is 0, it means you have nothing there. We'll not think about what is 0 power 0. Uh, Fine. So you have null, you have 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, and so on. You collect all these kinds of strings and put them in A. So A is some set of strings. And okay, one more understanding. So what is a language? What is essentially a language? Let's say there is no machine associated. What is a language? A language is any subset of sigma star. A language is any subset of sigma star. It is true, right? So look at this. Okay, here A is epsilon. Epsilon means null string. There is nothing there. Null string. 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1. It is very much obvious that A is a subset of sigma star, because A is a language and any language is a subset of sigma star. Because sigma star is a collection of all possible strings, it would mean language must be a subset of sigma star. That is very much obvious. So using pumping lemma, we just showed that, or we could show that the given language is not a regular language. Why? Because it is not satisfying the pumping lemma. So because A is not satisfying the pumping lemma, it means A is not a regular language. So what did we do here? We tried to split S into X, Y, and Z. So when we tried to do that, some contradiction came, I suppose. Yes. So condition 1 is not being satisfied. When I applied condition 2 and 3, it is not allowing me to apply condition 1. So that's the problem here. So I divided S like this one. I took a very general case. That's why K1, K2, K1 and K2 appeared. I took a very general case. It's like my Y has K1 zeros and K2 ones. But these zeros and ones it simply can't come from somewhere, no? So I have to take it from X and Z. That's why you have P minus K1 and P minus K2. If I apply my second condition, I got that K1 plus K2 is greater than 0. Size of Y essentially. Size of Y is K1 plus K2. Size of XY is, how much is it? P minus K1 plus K1 plus K2. You get P plus K2, right? This should be less than P. So K2 must be less than or equal to 0. But K1 and K2 must be what? K1 and K2 must be a whole number. So uh, a whole number that is less than or equal to 0 is exactly equal to 0. So K2 is 0. If K2 is 0, then if I substitute this above, I'll get K1 is positive. So my string after simplification, it will look like this. So X, Y and Z. Nice. So Y is 0 power K1. Nice. But if you notice, if since my Y is 0 power K1, if I try to apply the first condition of pumping lemma, which says x y power iz, so let's say I is 2, it would mean x y y z is also a part of the regular language, right? If I do that here, what will I get? Let's say k1 is some positive number, because let's say k1 is 1. So in that case, I will have 0 power p. No, if k1 is 1, I'll have 0 power p minus 1 and 0 power 1 and 1 power p. Will that be a problem? Okay, let me write the problem here. My string is 0 p minus k1. This is x. After doing some substitution and all, I got this one. Y is this one. And z is simply. Is that how it is? Yes. I mean, this is 1. Fine. Now I have to also verify if this is also a part of the given language for all I greater than or equal to 0. Let's say my I is 3, so that would mean my new s will become x y y y z. In this case, it would be 0 p minus k1, 0 k1, 0 k1, 0 k1 and 1 power p. But if you notice now, this will no longer belong to A, right? Because I should have equal number of ones and zeros, because that is how my A looks like. Because A is essentially 0 1, 0 0 1 1, 0 0 0 1 1 1, and so on. That is how my A is. So if number of zeros and ones has to be same, it would mean the sum should be same, right? This should be equal to this. But essentially, that would mean k1 has to be 0. So what is this trying to tell me? It's trying to tell me that my I can only be 0. My I can't be 3. Essentially, it's not allowing me to pump it. So pumping, in the sense, you're trying to uh, increase the number of times y appears. So that is why it's called pumping lemma. You're pumping y into s. So like you're pumping more. So you're putting y. So that is pumping lemma. You're pumping some substrings into the string. Mm, if k1 is 1, then what is my s dash going to be? My s dash is going to be 0 power p minus 0, 0, 0 times. So there is nothing here. 1 power p. I'm getting my same string back, but I'm unable to pump my zeros. And one more thing. So if k1 is 0, if you notice here, I can show it mathematically. K1 has to be strictly greater than 0, but then if I solve it, I'm getting K1 0. So there is some contradiction here. I'm unable to pump my string. So that is how we can show that A is not regular. Okay, I think we spent too much time here. Why did we spend too much time here? We have to go to the other important parts, right? So we'll go to the important parts. I was afraid I didn't tell DFA, but I did my part. I told DFA. Only NFA is not coming. So I won't tell pumping lemma for the other thing. There is one more pumping lemma. This is just a proof. You don't have to go through it. We know it is true. It is fine. If you wish to go through it, you can go, but that is fine. NFA, DFA. DFAs are simple to make. So maybe you could just go through the DFA at least, the DFA part. Why is NFA and DFA different? Because NFA can have multiple outputs for one transition, for one input to the transition function, but DFAs can't do that. Every input will have one unique output. Okay, so coming back to this, so we are using a DFA to solve the problem, which was checking if a pattern exists in a given string. So the given string is a t of it has length n, a string of length n, and then pattern is of length m, and presumably m must be less than or equal to n, because if m is greater than n, then that's a problem. The pattern will never be in the text, right? So we are defining a DFA. So what kind of a DFA? Okay, there's no drawing. Okay, there's no drawing. So we are defining a DFA. We are defining a DFA in such a way that uh, we have m plus 1 we have m plus 1 states. The idea behind having these states 0, 1, 2, 3, 4, 5, 6, so on until m, the idea behind this is that if you are at the ith state, it means you have successfully matched I characters before wherever you are currently. So that is the let me draw that. That is the idea. So if you have, this is the zeroth state. No, not. Uh, I won't write 0 here because it will deceive you. You would think that is the final state. So Q0, Q1, Q2, Qm. Fine. So the idea is, let's say this is the start state. So what does it mean? It means you matched with 0 characters. And if the input matches, if the input you read is the first character of the pattern, it means there is one match. So you move to match 1. If the next input that you read is the second character of the pattern, it means you got yourself another match. So mind you, these are coming from the input, they're not coming from the pattern. So if you're getting this from the input, it means there is a match, right? So the character matched with the pattern's characters. So you keep doing this, and let's say you stop at qi. So what does it mean when you are currently in qi? It means the previous uh, the previous I characters have been a match, and now you will read the next character, which is p I plus 1, or in the notes how it's there, in the notes how it is mentioned is this is state 0, 1, 2, and then finally you reach the state q. If you reach the state q, it means the previous q characters have been a match, and now you'll be reading the q plus 1th character next. So here I and I plus 1, in the notes I think it's q and q plus 1. We'll see. So that is the idea. So we want to construct that kind of a machine. What will happen if there is no match? That is a different story altogether. We'll see. So like we have to define a transition function in such a way that it also handles the cases when you have a mismatch. When you like, let's say you read q characters, they're match. What if the q plus one character is not a match? Then that's a problem. Then what is the transition function supposed to do? Since it's a DFA, for every input you're supposed to have an output, right? So if it's not a match, then what do you do? We'll see. We'll see what you're supposed to do. Start state is 0 because initially no characters have matched, so start state is 0. Final state is the set M because final state set of final states essentially is a set of final states. So in this set you will only have final states. For this problem we only have one final state. And what is the meaning? I told you, right? So if you're in the state q, it means q plus one if you're in the state q, it means you have q characters, which like you have q matched characters before wherever you are. So in the sense, uh, the previous q characters have matched. Yes, so the previous q characters have matched. If the previous q characters have matched, it means then you will find yourself in the qth state. So if you are finding yourself in the mth state, it means the previous m characters have been a match, and that's good news. It means the pattern exists in the text, because that is essentially what you're trying to solve, right? We want to check if a pattern exists in the text. How do you check this? If you read character by character, and if you get m matches, then you will find yourself in the m state. So what do you mean by m matches? It means you got p of m. So if you're reading the text, so how does text look like? It looks like t1, t2, t3, so on till tn. You're reading n characters, right? So let's say you're reading from here. Let's say this turns out to be p1, p2, so on till pm. It has been a match, right? So t3 turns out to be p1, t4 turns out to be p2, and so on. That would mean you found a match. So how does the machine know that you found a match? After reading all of this, where is the machine going to be in? The machine is going to be in the mth state, right? So if you read pm, you will find yourself in the mth state. So, and that is the final state. That would mean you found a match. So that is how the machine is going to know that you found a match. Okay, nice. Uh, all of that is nice. Uh, so we'll look at the first line. The first line is saying, first line in the sense, the last line of this page, transition q comma a. What does it mean? You're currently in the qth state. So what did I say when? Uh, what did I say that you're supposed to understand when you find yourself in the qth state? It means the previous q characters have matched. So it means the not the first character. You could be somewhere in the middle, right? So it doesn't have to start from the beginning. You could be somewhere in the middle, like this. You're reading from here. Like after some iterations, you found yourself here, and now you're reading. Uh, if you're finding yourself in the queued state, it means something like this. So until like one p1, p2, p3 till pq, you got matched characters. Now, so if this is t3, this will be tq minus 2. So you're currently reading tq minus 2. Now next you will read tq minus 1. Is it tq minus 2? Let me see. I think this is plus 2. Then this will be plus 1. Yes. So now next you will be reading t q plus 1, and currently you're in okay, after reading p1 you'll go to the first state, second state, the qth state. So you're currently in the qth state, and then you're reading this character tq plus 1. Now what is the function supposed to do? If it's a match, how do you know if it's a match? if the character turns out to be PQ plus 1, then it's a match. It means even the Q plus 1th character is a match. So then you will go to the Q plus 1th state. So that is essentially what is here. If the next character that you're reading, which is A is the next character that you're reading. If A is equal to the Q plus 1th character of the pattern, then it's a match. But here I wrote something else. Here I wrote if Q is not equal to M, because if Q is equal to M, it means you're already in the final state. So it it means, uh, see, if I don't put this condition here that Q not equal to M, imagine you're currently in the mth state, which means you're in the final state, and then you read your input letter A. So if I don't put this condition here, it would go here as well, right? So there is no M plus 1th state, because I only have 0, 1, 2, 3, 4, 5 until M. I only have M states. I don't have M plus 1 state. So it is only natural that I remove the uh, I remove the, what do I say, base case where Q is like, or extreme case. I remove the extreme case where Q is going to be M. So if Q is M, I will deal with it later. But currently, if uh, from 0 to M minus 1, if you find a match, then you move to the next state. So if you are currently at state Q, which means my previous Q characters have matched, and if I read the next character A, and if this next character A turns out to be the next character in the pattern, which is P of Q plus 1, then I go to the next state, which is Q plus 1. So if you're currently in the Q state, you go to the Q plus 1 state. Uh, so we have two more cases to think about. What if there is no match? What if A is not equal to P of Q plus 1? And what if Q is equal to M? So in those two cases, we are going to do the same thing. Uh, what we'll do is we will go to that state. So states are here essentially numbers, right? 0, 1, 2, 3, 4, 5, 6 until M. So they're all numbers. So length is also a number. So here we are going to that state which answers like, fine, let me just read this out. Length of the longest suffix of, uh, we have something new here. We have P of 1 comma 2 comma 3 so on until Q, and then A. So we have taken the suffix of the pattern. Suffix in the sense, you understand suffix, right? It comes to the, it's like the first half of a word. You understand what is a suffix, right? So I take the suffix of a pattern until the qth character, and then I concatenate it with the character A. So this is my new string. This is my new string. So I'm trying to find the length of the longest suffix of this new string, which is a prefix of the pattern P of 1 comma 2 comma 3 until M. So if you find this, then this will solve your problem. How is this solving your problem? The idea here is that let's say you're reading some string, right? T1, T2, T3, T4, TQ plus 1, TQ plus 2. Wait, this is going to be TQ plus 3, right? Yes, TQ plus 3, so on, TN. So let's say you read you begin at state 0, right? You start at state 0, 0. Let's say that is 0, because that is, I'm not writing 0 properly because you get confused. Is it the final state or not? So I'm just writing that way. Let's say T1 is not equal to P1. P1 means P of 1. So I'm just writing it in a short, I'm just using short form. Fine. So what would you do in this case? If the first input character is not P1, then you remain in 0, because what does the 0th state mean? It means uh, currently zero characters have matched. Let's say this turns out to be this doesn't turn out to be P2, so you still stay at the zero state. Let's say this turns out to be let's say T3 turns out to be P1. So it means now you found one match. So you have to go to state 1. So what does it mean when you're in state 1? It means you have one consecutive match. You have one consecutive match. Because if you find something else in the next place, if you don't find P2 in the next place, it means it's a mismatch. So let's say you found P2 as well in the next in the next character. So what does it mean? Now you'll go to state 2. What does it mean when you're in state 2? It means consecutively you found two characters that have matched. And let's say this goes on until here PQ. So Q characters are matched. Let's say you reached the queued state. So which means Q characters are matched. Now what you're supposed to do? You're supposed to check if the next character is a match or not, right? So what is the next character? We have a next character. This is the next character, and you're currently in the queued state. Now you have to check if this is equal to PQ plus 1. If it is PQ plus 1, then you will go to the Q plus 1 state. Now let us suppose this is not PQ plus 1. Now what do you do? Until here we got a match. Suddenly we're telling no match. We didn't reach M. We have to reach M, right? Because pattern has M characters. Pattern has M characters, but Q is somewhere. So we stopped in the middle. We got a match until here, but there is no match. Because even if one character is different, it's not a match, right? So this is not a match. So what do we do now? The idea here is uh, like in what did we do in the naive method? We slided this window and went to the next one, right? But uh, this is a machine. We're dealing with I should say maybe numbers. So I don't think there is any concept of sliding, but we will imitate that part here. We'll see how. Because if you notice, we were like, what did we say? Length of the longest suffix of this one, which is a prefix of this so and so pattern. So the idea here is simple. I don't know. I didn't get it for the first time. I had to sit for a while and think about this. Okay, let me write it here. Length. If mismatch is there, if Q is equal to M, or if mismatch is there, mismatch in the sense if I'm reading this one, no, delta Q comma A. I know what I'm supposed to do if my A turns out to be the next character, right? A or else given that uh, this shouldn't be M because I can't go to the M plus 1 state. So if there is a mismatch, so what does it mean if this condition failed? It means A is not equal to the next character in the pattern, or Q is equal to M. So that is the meaning of else here. So what do? I wrote you go to the state, which is like the state is a number, right? So length is also a number. You go to that number. Which number? Length of the longest suffix or prefix suffix yes, so length of the longest suffix of this new string, which is p of 1 2 3 4 q. We had a match until this string, right? So you concatenate it with a. We'll see why is this true. Suffix of this one, which is also a prefix of the pattern. Pattern is 1 to n. Fine. So the idea behind this is, where were we? We got a match until here, right? P1 to PQ, we got a match. And the character that we are reading is A now. Now the idea is, now that this is not a match, now I have to like go forward. Now what do I do? What is the next step? The next step is uh, if we look at what we did here, we did some concatenation, right? P of 1 2 3 till Q until A. So where is this? This is essentially this one. This is nothing but P 1 to Q concatenated with A. This is fine. I have to check the longest suffix of this, which is also a prefix of. Okay, now how do suffixes of this string look like? So suffixes of the string are basically the string itself, or else uh, you will get. Okay, I mean, okay, did I say suffix is the first part? My bad. So suffix is the next part. My bad. I think I told suffix is the first half of a word. My bad. So suffix is the next half, or not half. It could be just the next part. So suffixes look like this. So if I remove one character, it's going to look like this. If I remove two characters, it's going to look like this. If I remove three characters, four characters, these are all suffixes. So I'm basically removing the characters from the front, and I'll get suffixes. So we understood what is a suffix. So what are we supposed to find? We are supposed to find the longest suffix of this concatenated string, which is also a prefix of uh, the pattern P of, basically the pattern. This is the entire pattern, right? So so what does it mean? It means now that this is a mismatch, now check. I'm crossing out T3. That means now this is my suffix. This is my suffix. Now I'm checking if this is a prefix of the pattern. It means uh, I'm checking if this is coinciding with the pattern. So I have a string here. I suffixed it with A. Now okay. I'm removing this, and then I'm checking if this matches with the pattern or not. Okay, let me begin again. So I have a text which is nothing but P1, 2, 3. I had a match until Q, right? And my eighth character, not eighth character, my character A did not match. So I have this. This is my concatenated string. So I'm checking if its suffix matches with. Okay, fine. So this did not match. So what I'll do is I will cut the first character and now check if it is matching with my pattern P. I'm checking if is this new thing a suffix, if this new thing is a prefix of my pattern, because my pattern could be longer. So I'm checking if this is, I'm checking if there is a match here. So if there is no match, what I'll do is I will proceed. I will cut one more character and now check if my suffix of the concatenated string is a prefix of the pattern. This is the suffix of the concatenated string. This is the prefix of the pattern. So now I'm checking if the suffix of the I keep repeating this process. Let's say this turns out to be a match. Let's say this turns out to be a match. Now, what does it mean? I told you that if you're in state Q, if you're in state Q, it means Q characters have matched. Now I'm telling you the suffix of this concatenated string matches with the pattern. I mean, not the entire pattern, the prefix of the pattern. That would mean the length of this suffix will give me the number of characters matched, and that is essentially the state. So go to that number. So if the length of this suffix is, let's say, 5, then go to state 5, because state 5 represents that 5 characters have matched. So that is how that is why we do this. Why longest? Because you want the longest match, right? You wouldn't want to uh, you wouldn't want to cut many characters and be like one character match. It's better if you have more number of characters match, right? So you start from the largest number and keep cutting down. So see, if you have 5 matches, it means you also have 4 matches, you also have 3 matches. So essentially you have to find the largest number. So that's why you have to find the length of the longest suffix of this concatenated string, which is also a prefix of the pattern. Find the length and go to that state, because here my states are essentially numbers 0, 1, 2, 3, 4, 5, 6, 7, 8 till m. So nice. So I told you that even if q is equal to m, that means after you reach the final state, if you read any character, you repeat the same process. Because what does it mean if you're in state m? If you're in state m, it means currently all of this is matched, fine, and then you read a new character a. Now there is a possibility that this suffix, no, see, its size is m plus 1, so this will not match with the pattern. So now you have to take the suffix of this and check if it is matching with the pattern. So same process, you continue the same process. If it is not matching, then you take a new suffix. If it is not matching, take a new suffix. If it's not matching, take a new suffix. If it's a match, then stop there. Find the length of that suffix and then go to that state. So if this length is 5, go to state 5. If this length is 3, go to state 3. So I think we spent some time here as well. So that is the idea when, I mean, it's here, right? So suffix, prefix. You're checking if the suffix of my concatenated string p1 to q along with a is a prefix of p1 to m. I think this diagram is simpler, no? So this you keep checking if that's happening or not. If there's no match, then you decrease the size of the suffix. So finally, if I keep decreasing, what's going to happen? If there is no match at all, I will reach 0, because I will exhaust my concatenated string, and 0 means 0 match. So nice. So if you get 0, then you go to the 0th state. But the idea here is, if you get a mismatch, don't directly go to 0. You go to this number, the number which is represented by this one, the length of the longest suffix, which is also a prefix. Nice. I spent time here because okay, fine. So this is how you uh, let's say write the transition function. Like, see, transition function means it's not going to compute everything on spot, right? So in this case, what we're doing is we're checking all possible cases and storing it in our let's say some kind of a 2D matrix. Some it looks like I maybe some kind of a 2D matrix, because function we've seen this one. Where is this? Here, see, this is a 2D matrix. So deltas can be represented as 2D matrices. So in this case, rows are representing the input characters and columns are representing states. You can interchange the order; it wouldn't matter. So where was it? You could try taking an example, and could try constructing a machine. Okay, what is the time complexity of this? So if you already have your transition function ready, so accessing a 2D matrix will, you can do it in constant time, right? It's a 2D array. I mean, a 2D array, yes. So you can do it in constant time. So if your transition function is already ready, then what is happening here? Computation is basically checking if your next character is equal to p of q plus 1 or not. So only one checking is happening. So by the time you finish reading the input, you will get an output as to if there's a match or not. So that's why it's OFN. So OFN is the time taken to read the input, right? And after reading the input, you'll directly get your answer. So that is OFN. But in case your delta is not, mm, let's say it's not ready beforehand, so you're supposed to make it. How do you make it? You use this algorithm. So what is the time complexity of this? You're going through uh, m plus 1 states, right? Here m is the size of the pattern, so that's why you have size of p, and then you're doing this for every character in the alphabet, so size of the alphabet, and you're checking if one string is equal to the other string. So basically you're checking if the suffix of your concatenated string is matching with the prefix of the pattern. So that would take around the order of the size of the pattern. And here I wrote size of the pattern square. Why is that? Okay, so k ranges, k goes on, right? K keeps increasing. It goes from uh, at most it would go on until m. K could at most go on until m. So this comparison inside the while loop takes around size of the pattern, and this k could go from 1 to m, which is again the size of pattern. So order of size of pattern square, that's why you have it there. So total time complexity will be this much: size of p plus 1 into size of sigma into size of p square. And then if you're reading the input, you'll have to read the input, so you'll get extra n as well. So you won't get all of this if your sig not sigma, if your delta is already ready. But in life it won't be that way, right? You'll have to make your own delta. So nice. So if you look at this, it's like for every pattern there is one machine. Based on the pattern that you have, you create a machine. So if your pattern is of size m, then you will create an m plus 1 state machine which follows all of this. And you create the machine only once, right? Now you can check in any number of in like if, let's say you have 1,000 texts and you want to check if a pattern is in each of those texts or not. So you create this machine only once, so you will get your delta. Now you can check if this pattern exists in each one of those texts in linear time. Checking is in linear time, it's only creating this delta function that's taking a lot of time. So if you remember, Rabin-Karp takes only so and so time. So in Rabin-Karp we are converting everything to numbers, right? Yes, so numbers. So that this is the time complexity: size of text minus size of pattern plus one times size of p. But if you look at it, this machine that we constructed, this DFA, it looks like it's taking a lot of time, isn't it? How in the sense my my time complexity of the machine depends on the size of the alphabet, whereas that is not the case in Rabin-Karp. Size of the alphabet, size of sigma, right? Size of the alphabet, size of sigma. So if my size of the alphabet is very large, my machine is going to take a lot of time trying to construct this transition state. So why even use this? Why even use this machine? The advantage comes when you have to uh, check if the pattern exists in a very large number of texts, probably. So let's say you have 10,000 strings that you want to check the pattern in. So in that case, so why does it become better in that case? Because in that case, see, you construct the machine once, and then you can check in all of those things in linear time. But that is not the case in Rab and Carp. Rab and Carp, it's the same time complexity. For every string, you have to perform this much. So at one point of time, this uh, this DFA that we constructed is going to perform better. So for large input, my DFA is going to perform better than Rab and Carp. So there was this term like this, you construct this for one time and then you use it again and again. It's called, I think, not I think, sir did mention, it's not in the notes, amortized time. I think Americans will write Z, but that's not an issue. Uh, Fine. So this extra time, this p plus one size of sigma, I think this part is amortized time. You do it only once. Uh, okay. PDAs, I don't think, not I don't think, it's mentioned in the mail that they won't ask us any questions on PDAs. So now it's like, okay, I'll just tell the basic. What is a PDA? A PDA is basically, it's a DFA only, but then now you have some memory that you can store things in. So you have a stack in this case, but stack is like kind of limited, right? Because if you store data in it, you can't access something that's in between the stack. You can only pick something that is on top of the stack. So you push and pop. You can't take anything in between. So that is a restriction. So it's like you have infinite memory. The stack has infinite memory, but you have limited access. You have restricted access. So, but DFA has no memory at all. So DFA can't store anything except the states. It has nothing else. I mean, it's not storing anything in the sense. It's moving from one state to the other. But in PDA, you have infinite memory, which is the stack in this case, which means you have restricted access. You can't pick any element that you want. But an array is different, right? Array, there's no restriction. You can access any element you want. And we have some notation, fine. So can I say that every DFA is a PDA? Yes, you can. So how does that work? You just say that DFA is doing its own thing, but it's not using the stack. So that way you can say every DFA is a PDA. But is every PDA a DFA? No, because if PDA is using a stack, then I can't represent that using DFA. But DFA not using the stack can be represented using PDA. That is fine. So this tau is the new addition. Tau is basically the stack. It represents the stack. Represents the stack in the sense represents the letters on the stack. So this is the stack alphabet. So sigma is the input alphabet. Tau is the stack alphabet. It means, okay, why do I have two different alphabets? It means I can now have some special characters that may not exist in sigma. I can have some special characters that may not exist in sigma, and I can use them. I can use them to store it in my stack. So that is an extra benefit. You can have extra characters. One example is it's in the other page. One example is the dollar sign. So we use the dollar sign. The dollar sign is basically the null character of the stack. You can think of it that way. It is used to check if the stack is empty or not. So that is the purpose of dollar sign. Uh, Notation is fine. So it's like I'm okay. If a comma b gives, I mean, they won't ask us questions in PDF, so I'll just it's fine. So I'll just go through this. So languages So the set of strings, so the set of, see, so the set of strings accepted by a PDA is called context-free language. So if any machine has a language, and in particular, if a PDA has a language, that language is context-free. So nice. So even this has deterministic and non-deterministic versions. I wrote it here. The transition function changes everything. So how is it non-deterministic? Okay, here you have three inputs, right? You read the state. Three inputs. What are the inputs? You read the state. You read the state in the sense check which state are you in currently, and then read the input character, and then read the character on the stack. So you have three options. And the output is going to be state. So state is which state are you going to go into? Not you, the machine. Which state is the machine going to go into? And the other tau is if you change the stack, if you change the element on top of the stack, what is that element? So the new output. So the function outputs the state into which the machine is going to go into. No, the state into which the machine is going to go, and the new character that's going to go onto the stack. So see, previously it was just q cross sigma gives q, right? You have a tau extra now because now you're dealing with the stack. You read from the stack, you give input to the stack, you give output to the stack. So two things are there. You read from the stack, and then you can change the elements of the stack from the top, at least. Not at least, at most. You can't change it from anywhere else. Deterministic is like now you have other possibilities. Other possibilities means, in the sense, for one input you can have multiple outputs. So for one, this is not a doublet now. This is like a triplet. Now you get three inputs, and then you have a subset of the power set. So not subset. You have an element from the power set, which is essentially a subset of pairs. So you can get let's say q1 comma, okay, let me say stack alphabets t1, so q1 comma t1, or else q2 comma t2, q3 comma t3. You can have multiple outputs for a given input. So let's say my input is q naught comma s naught comma t naught. So if my input is q naught comma s naught comma t naught, my output can be q1 comma t1. If it's non-deterministic, you'll have more outputs. You can have q1 comma t1 and q2 comma t2 and then q3 comma t3 and so on. Fine, enough of PDA. Okay, so the language that we saw before, which was proved to not be regular, it turns out to be a context-free language because we were able to build what kind of PDA is this? This is a non-deterministic PDA because if you notice, uh, if I'm at start state Q1 and if I read, is this non-deterministic? No, I mean, you would only use epsilon if you're in non-deterministic. Usually, I don't think in deterministic you would use epsilon. Nice, fine. So it's like, okay, I'll give you an example. So 0 comma epsilon arrow 0. It means if if you read the symbol 0 and you don't pop any, that was the convention, right? You don't pop anything from the stack, you push 0 onto the stack. That was the convention, no? Where is this convention? Here. So you read from input, you pop from stack, you push in onto stack. So that was the convention. Nice. So I think this is a non-deterministic PDA, but I don't think they'll ask us questions. uh, Oh, we've spent like 1.5, 2 hours. Uh, Fine, I'll just. Okay, apparently, PDAs are like deterministic and non-deterministic versions are different. But DFAs and NFAs are equivalent, that is fine. I'll not go through pumping lemma of this because they told they won't ask questions. Okay, now we are entering the Turing machine region. So here we'll answer the question, uh, not answer the question, we will prove the statement, which is this one. There are countably many Turing machines, but uncountably many problems. So we will try to prove that now before knowing what is a Turing machine. Yes. So let's say sigma is nothing but 0 and 1. It means I'm going to deal with binary strings. So where are my binary strings? All my binary strings are in sigma star. So all my binary strings are in sigma star. If L is a language, then L is a subset of sigma star. If any language is there, it's going to be subset of sigma star. That is very much obvious. Subset in the sense, for example, let's say, what is in sigma star? You have epsilon, uh, 0 1 0 0 1 1 and so on. I can make any subset, right? So let me take one subset, 0 comma 1 comma 1 1. So this is one subset. 0 comma 1 comma 1 1. This is a subset of sigma star. This is a language, and this is solving some problem. See, languages are equivalent to problems. So this is solving some problem. What problem it is? Now you're supposed to know. I wouldn't know. Okay. Anyways, I mean, you get it, right? So languages are essentially subsets of sigma star. That is very much uh, trivial. Nice. So let's say now I want to count the number of languages. So that's why I wrote hash there. So hash set of languages. So I just want to find the number of elements in the set of languages. So I just want to count the number of languages. I told you languages and problems are the same thing. So number of languages equal to number of problems, or in other words, the number of elements in the set of problems. They're the same thing. Now I told you language is nothing but a subset of the powered set, right? Sorry, subset of sigma star, right? Language is nothing but a subset of sigma star. Now, if I'm trying to look at all possible languages, I could also look at all possible subsets of sigma star. Because if language is essentially a subset of sigma star, then all languages would mean all possible subsets of sigma star. So number of languages is also equal to the number of elements in the power set of sigma star, because power set of sigma star contains all possible subsets of sigma star, right? So one thing that we can establish is the number of problems is equal to the number of elements in the power set of sigma star. One more thing, this is fine. Every machine can be represented as a binary string. See, what is a machine? A machine can be mathematically represented, right? For example, let's say DFA. DFA is a five tuple. So in that five tuple, what do we have? We have capital Q, we have sigma, small q naught, uh, the transition function delta, as well as capital F, the set of final states. Now I can represent each of these mathematical objects in zeros and ones. See, all the information that we're see, you understand it. I can convert basically anything to zeros and ones. So I will convert the description of that machine into zeros and ones. So that is essentially a binary string. So I can represent every machine as a binary string. Because see how is the machine described? Using a five tuple for DFAs, six tuple for PDAs, uh, A Turing machine is a seven tuple. We'll come to that. So everything I can represent in terms of a finite binary string. So fine. And if this is a binary string, what does it mean? Sigma star, I told you, sigma star is a set of all possible strings over sigma. And sigma turns out to be 0 and 1. So sigma star is nothing but the set of all binary strings. And I told you that every machine can be represented as a binary string. That would mean if I sit and what do I say? Uh, what did I say? If every okay, yes. So every machine is a binary string, right? So it would mean this binary string will be somewhere in sigma star. This machine's description in binary string will lie somewhere in sigma star. And Turing machines is some kind of a machine. It need not be all machines, right? So Turing machine is some set of machines with some conditions, some special properties. So it would mean if I sit, we don't know what is a Turing machine yet, so we'll see. So if I sit and collect all Turing machines and keep them in one place, so essentially it is also a binary string, right? So I'm just collecting some binary strings. I'll just put them in one place. So this will be a subset of sigma star because uh, if I collect some binary strings, it's going to be a set of binary strings, and any set of binary strings has to be a subset of sigma star, right? Yes, because if you have a set of binary strings, here sigma star is a set of all binary strings. So that would mean any set of binary strings has to be a subset of a sigma star. So the set of Turing machines is a subset of sigma star. Nice. Now we will see more details. So let me try to uh, enumerate. Is enumerate the right word? Okay, let me try to number the elements of sigma star. See, set is a collection of unique elements. There is no order, right? So now what I'll do is I will fix the order. I will fix the order of the elements in sigma star. So what is sigma star? All binary strings, right? So I have epsilon, 0, 1, and so on. And if I'm fixing the order, what does it mean? It means I have a first element, second element, third element, fourth element. In other words, there exists a bijection from natural numbers to sigma star. Because what is natural number? One, 2, 3, 4, and so on. And here, what am I telling? There is first element, second element, third element. That would mean there is a bijection from natural numbers to sigma star. That would make sigma star a countable set. So that is why I wrote countable there. So now we understood sigma star is a countable set. And any subset of a countable set is also countable. So the set of Turing machines is a countable set. That would mean there are countably many Turing machines. So we proved one part of the statement. There are countably many Turing machines. Now we have to show that there are uncountably many problems, which we'll come to in a moment. Suppose, and we know number of problems equal to number of elements in the powered set of sigma star. We've just seen previously. So let us suppose the powered set of sigma star is countable. That would mean now I can say, okay, what does powered set of sigma star have? Powered set of sigma star will have subsets of sigma star, and any subset of sigma star is a language. So that would mean power set of sigma star has languages as its elements. Now, if I say power set of sigma star is countable, that would mean I can now number my languages. First language, second language, third language, fourth language, and so on. I can order the languages in the power set of sigma star. So I can, okay, enumerate. I used enumerate. So I enumerated the languages. So language 1, language 2, language 3, and so on. Because I'm assuming it's countable, so I can do this. Uh, now, Now what I'm going to do is like how we represented machines as binary string. There is a way in which I can represent the language itself as a binary string. How can I do that? So for example, let's say I have sigma star, right? Sigma star has epsilon 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, and so on. And see, languages are, see, I'll give you an example. Languages, this is one language. Uh, this is one more uh, language. I have so many languages. I can have multiple languages. So what I'm going to do is I'm telling you that I'm going to convert the languages into binary strings. How am I going to do that? You think I'm going to concatenate all the elements? No, I'm not going to do that. That will not give us unique binary strings. What I'll do is I will assign some. Uh, I mean, I told you that I fixed the order of sigma star, right? So this is nothing but 0, 1, 2, 3, 4. Uh, or fine. I'll start at 1, 2, 3, 4, and so on. It goes on, right? First character, not first character, first string, second string, third string, fourth string, and so on. So what I'll do is I'll show you how I'll represent this language as uh, a binary string. So what I'll do is I will check the first character. Is the first string is the first string in sigma star also in L1? No, epsilon is not there, so I'll put a 0. Then I'll check if the second string is in L1 or not. Second string is 0, 0 is there, so I'll put 1. Is the third string in L1? Yes. Is the fourth string in L1? Yes. Is the fifth string in L1? No. Is the sixth string in L2? L1? No. Is the seventh string there? No, 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 and so on. So what I just did is I converted my language L1 into an infinitely long binary string. And this is unique. For every such binary string, I can get back my language. For example, if I have a binary string that looks like this, I can get back my language. My language is going to be the second character, second string of sigma star along with fourth string of sigma star. Second string is 0 and the fourth string is 0, 0. So this is my language. So vice versa, they're one-to-one mapping. For every infinitely long binary string, there is a language. For every language, there is an infinitely long binary string. That is what I, oh my bad. That is what I wrote here in words. That is what I wrote here in words. So what I did here is first I enumerated the elements of power set of sigma star as language 1, language 2, language 3, and so on. So each language is a subset of sigma star. So what is it that I'm doing now? I'm converting each of these languages into infinitely long binary string. That is what I did here. I showed you how to do that. So now what does it mean? Now there is a mapping between the elements of the power set of sigma star to the set of infinitely long binary strings. So they're all infinitely long binary strings, right? What I'll do, I'll collect all of them and put them in a set called B. So now B is the set of infinitely long binary strings. And just now we showed that for every infinitely long binary string, there is a language, and for every language, there is an infinitely long binary string. So there exists a bijection between uh, B and the powered set of sigma star, because all of these are elements of the power set of sigma star, and all of this is happening because we assumed power set of sigma star is countable. That is why we have language 1, language 2, language 3, and so on. If it's not countable, then we can't do that. But by assumption, by our assumption that power set of sigma star is countable, we can do this. We can enumerate the elements of power set of sigma star as language 1, language 2, language 3, and so on. Okay, now what I will try to do is uh, now I will try to prove that B is uncountable. I will use proof by contradiction. So let us suppose B is countable. So if B is countable, now I can enumerate what is B? B is the set of infinitely long binary strings. So if I say B is countable, now I can enumerate each of the infinitely long binary strings. So they're all strings. So I'm enumerating them as S1, S2, S3, and so on. and each string is an infinitely long binary string, right? So I have B11. B11 is the first bit, second bit, third bit, and so on. B11, B12, B13, B21, B22, B. I have infinitely many bits in this binary string, so it goes on. So now what I'll do is I'll do something very similar to what we did while we were trying to prove the interval 0 comma 1 is uncountable in DMS we did last time, right? So very something similar that I'm trying to do here now. I'm constructing a string S with the bits B1, B2, B3 and so on, such, such that BI is not equal to BII for all I. So what does it mean? So if BI is not equal to BIA, it means B1 is not equal to B11. It means S is not equal to S1. B2 is not equal to B22. It means S is not equal to S2. And S is not equal to S3. S is not equal to S4 and so on. It means S is not equal to any of the SIs. It would mean S is not a part of B. But S is also an infinitely long binary string. S is also an infinitely long binary string, but it is not in the set of infinitely long binary strings. That is a contradiction. So why did this contradiction come? Because we assumed that B is countable. Hence, B is uncountable. And if B is uncountable, that would mean something else is also uncountable. What is that? We showed previously that there exists a bijection between B and the power set of sigma star, right? So if B is uncountable, that would also make uh, the other one, which is the power set of sigma star, uncountable, because there is a bijection, there is a one-to-one mapping. So whatever is true for B will also be true for power set of sigma star, only because there is a one-to-one mapping, which is one-to-one and onto. So there is a bijection between B and power set of sigma star. So finally, we proved power set of sigma star is also uncountable. And if power set of sigma star is uncountable, what else is uncountable? Power set of, see, the number of uh, what does it mean if this set is uncountable? It means there are uncountably many elements in this set. There is no bijection from natural numbers to this set. So I can't count them as 1, 2, 3, 4, 5, 6. There are more. It's like you understand what is uncountable. There is no bijection between natural numbers and this power set of sigma star. And what did I say about the number of elements in power set of sigma star? It is nothing but it is equal to the number of problems that exist. So, in other words, if I rephrase it, I can finally say that uh, there are uncountably many problems. So, now we proved the entire statement. There are finitely many Turing machines, but uncountably many problems. We did not go through what is a Turing machine yet. We'll come to that soon. So, sigma star is countable. So, there are finitely many Turing machines, because set of Turing machines is a subset of sigma star. So if sigma star is countable, then any subset of it must also be countable. So set of Turing machines is countable. We proved that power set of sigma star is uncountable. So set of problems is uncountable. So uncountably many problems, but only countably many Turing machines. You can ignore the text on the top here. Okay. Yes. Oh, I could write here. I could write here. My bad. I'm just realizing it now that I could write here. Uh, Fine, no problem. Uh, so there is an alternative proof as well. You can go through it. So okay, fine. That was like a theory question. Like uh, fine. This is another way to prove it. You can see. Okay, Turing machine. We have now currently we have uh, we already dealt with DFAs, NFAs, and PDAs. So this shouldn't surprise you. So that is one advantage of going through all of them before, instead of directly opening Turing machines and looking at all this text. So we have a basic idea as to what is DFA, PD, and all of those things. So most of this is almost familiar to all of you. So the only thing that changed is there is no set of final states, and you have three small queues in the seven tuple. So we'll just go from the starting. Turing machine is a seven tuple. So this is also a mathematical object. How do you represent this? You have seven things in a tuple in an order. So what is the first thing? You have capital Q, the set of states. You have sigma, input alphabet. You have tau, the tape alphabet. So in PDA we had a stack. In Turing machine we have a tape. We have an infinitely long tape that looks like this. There is a tape. It starts here. I mean, this is where it starts, but then it's infinitely long. So essentially, you have uh, infinite memory, don't you? Like stack, you have infinite memory. But unlike stack, there is no restriction here. You can access any part of the tape. So the representation of a Turing machine is uh, this is your current state. You have a current state, and then you have an arrow that's pointing. You have an arrow that points to. It's like I think this is called something. The tape head. I think I think it's in the notes. Tape head. It just points to a portion on the tape, and in the beginning the tape will have blank characters. So this blank character is not an input alphabet, it belongs to the tape alphabet. So you have special characters. The idea behind having tape alphabet, stack alphabet, and so on is that you can have special characters. So in PDA we had dollar sign, uh, and in non-deterministic versions we are using something called epsilon to represent empty string. And then in Turing machines, more specifically, we have the blank character which belongs to the tape alphabet. That is fine. So, okay, what else do we have? We have a capital Q, we have sigma, we have tape alphabet, we have Q start. Q start. Q start is the starting state which belongs to capital Q. Then we have our delta. We'll look at it. We'll look at the transition function later. We have Q accept, and then we have Q reject. So previously we looked at like final state capital F, right? Here you don't have a set of final states. Here you have Q accept, Q reject. So the Turing machine, how does it work? Is the moment it enters Q accept, computation is going to stop. Like the machine's going to halt. That is the property of Turing machine, and it's going to halt. No more computation is going to happen. And since it enters Q accept, it accepts the input irrespective of whether there is more input or not. So it's like, let's say you're eating food, and then let's say you're no longer hungry. So irrespective of whether there is food on your plate or not, you're going to stop eating. So something like that. So the moment it enters Q accept, the Turing machine is going to stop. So it's going to halt. And the input is considered to be accepted. Now let's suppose it enters Q reject. Same story, but the input string is rejected, irrespective of the irrespective of the unread input characters, irrespective of how much more input is there. The moment it enters the Q reject state, the Turing machine, whatever is there here, the Turing machine is going to reject the input, the entire input. Now, in DFA, we didn't require all of this because in DFA, you have to read the entire input. Only then you will know, okay, this is accepted. How do you know it's rejected? If it doesn't find itself in the final states, then the DFA considers the string to be rejected. But here, unless you enter Q accept, you wouldn't know if the string is accepted or not. And just because the string is not accepted, it doesn't mean the string is going to be rejected, like in the case of DFA. Because if the string for the string to be rejected, the machine is supposed to enter Q reject state. So there is this possibility where the machine keeps looping around, like looping in the sense it keeps going in cycles. It transitions from one state to the other, but it never reaches Q accept. It never reaches Q reject. It keeps going on in cycles. So this is one possibility. This is one possibility. We'll come to that in a while. But okay, now we are just seeing what is a Turing machine. There is input alphabet. There is tape alphabet. Here I wrote something. Uh, Tape alphabet minus sigma is not equal to 5. So basically, I'm telling that if I remove all the uh, input characters from tau, which means the tape alphabet also has input characters. Okay, why must the tape alphabet have input characters? Because tape alphabet, see, what is tape alphabet? It's like the alphabet that, it's like from this set you will use the characters uh, which you will put on the tape, right? You can write on the tape, you can delete characters on the tape, you can see what can you do with it. You can write, you can remove, you can replace, whatever. So the alphabets that you use there come from the tape alphabet. Input alphabet is basically, it's like some string is there, right? You're getting some input, so that is represented by sigma, the input alphabet. So tape alphabet is like, you have storage now. So tape alphabet. In DFA we had nothing like that. In PDA we have stack alphabet. Here Turing machine you have tape alphabet. There is nothing much. So the meaning of this being non-empty is that you will always have special characters. So if I even if I remove all the input characters from the tape alphabet, you will always have special characters. For example, here blank. Where is blank? Blank symbol. You have a blank symbol. Blank symbol belongs to tape alphabet. And I also wrote that sigma is a subset of tau. It means the input alphabet is always a subset of tau alphabet. It means my tau alphabet has all the characters from sigma along with extra characters. So that is the meaning. For example, see, in front of your eyes, you have the blank symbol. This blank symbol is an extra character that you won't find in sigma because the input is only a string. It's not going to have any space or anything. It's just a string, a collection of characters. That's it. Normal input characters. Whatever is in sigma, from sigma star, you'll get your string. Whatever is a string, that's going to be your input. You won't have special characters there. Uh, okay, so Q start, Q accept, Q reject belong to capital Q. This is trivial. It's like if it's not in capital Q, then where else is it going to be? It's supposed to be in the set of states. It's supposed to belong to the set of states. And Q accept is not equal to Q reject. This is yes, because you can't have the machine saying that the given input is both accepted and rejected. So to avoid such problems, we have to define Q accept and Q reject in such a way that they are not the same states. Okay, transition function. How does the transition function of a Turing machine look like? Uh, Capital Q cross tau. So you have uh, two inputs. So two inputs in the sense you will look at your current state. So this is what I'm talking about. Two inputs in the sense you have the current state. This is, it will check which state are you in currently, and then it will check the letter which is pointed to by the tape head. So wherever the tape head is pointing, it will check that portion of the tape. It will check what is the character that the tape head is pointing to. And yes, this tape head can be moved. It can go right. It can't go left if it is here. So let's say if the tape head is here, you can go right, you can go left. You might get a question: can it stay in the same place? Uh, that is a different Turing machine. But if you want to mimic staying in the same place, you go right and then go left. So that means you came back to the same place. So we'll just see that. We'll just look at the transition machine. So input is you read a state and then you read the character that is pointed to by the tape head. So what is the output going to be? The output is the state is going to change. So there'll be a state there, and you might change the character, right? After reading the tape, you might, after reading the character from the tape, you might change the character or replace it or do nothing, whatever it is. So the output will also have the tape alphabet. So you have Q, your change is stating, your change is stating. Your state is changing, my bad. Your state is changing. and the character in on the tape is changing. And the other thing here is left or right. It means after reading the input, as a part of the output, you also either move the tape head to the left or to the right. So this is also a part of the output. So output, what is happening? State is changing, your tape is changing. Tape is changing in the sense a character on the tape is changing, and the position of the tape head is also changing. So that is the output. Input is you read the current state, you read the tape. Output is state is changing, the character on the tape is changing, and the position of the tape head is also changing, left and right. This transition function does not exactly represent the transition function, because there is one small exception, that if your tape head is at the first location, then it can't go left. So that is one change which is not represented here, but it's fine. It's fine. uh, this is an example. So if you're in state q1, and the tape has the letter b, here the output turns out to be state q2, and the letter is changed to C, and then you move right. So how does it look like? So let's say you're in state Q1, and then your tape is pointing to the character B. I kept no other characters. It means that there is blank symbols all around. So after the transition function does its job, uh, I said that it goes to state Q2, it replaces B with C, and then it is going towards the right. So tape head is now pointing to the right. So this diagram that you've just seen, uh, this is one configuration. This is one configuration. This is one more configuration. So it's like if you take a snapshot of the Turing machine, that essentially becomes your configuration. So here you have two configurations. And below this is the notation. The notation goes like, this 1 minute. The notation goes like this. So how there is a notation for the configuration. No, let me just keep this. So if you have no, if you have the tape, and then let's say let's say this is your current configuration. So the notation is like this. You write everything. So you write A, you write B. Next is C, right? But C is the character that the tape head is pointing to. So before writing C, you write the state Q, and then you write C. It's like Q is pointing to C, and then you write D, and then that's it. It's like this is your configuration. So you can call this configuration 1. So that is what I wrote here. So here I have all blank characters, right? And my tape head is pointing to B. So before B, my Q1 will come. So I captured the configuration in one line. So blank character Q1 B blank character, that is fine. Here my configuration changed, right? So I write everything before the tape head. So what is before tape head? Blank character and C. And then now my tape head is pointing towards the blank character. So before I write that, I will write Q2 and then write the blank character. So before the character that the tape head is pointing to, you mention the state as well. So that becomes your configuration. It's just representation. So you're representing it. Fine. And yes, so the configuration. So this is an example. Configuration. I wrote it here. So A, before B you have to write Q, because that is the character which is pointed to by the tape head, and then C, fine. And okay, exception is understood. You can't go left if you're at the leftmost position. Yes, and machine halts when Q accept or Q reject is reached. And the machine will keep on processing the thing if you never reach Q accept or Q reject. So, okay, this is like uh, instead of left right, you also have stay. So, is that going to change? Uh, Turns out both of them solve the same set of problems because I can mimic the stay by simply going right and then going left, or going left and then going right. So, I can mimic the behavior. So, both of them are equivalent. Equivalent in the sense, equivalent in uh, solving problems. Like they solve the same set of problems. Their solving powers are the same thing. They solve the same set of problems. Oh, is this the last page, I suppose? Yes. After this is the part that I'm supposed to tell you. Hmm. Okay. Fine. And single tape, multi tape, they're also equivalent. Equivalent in the sense they solve the same set of problems. Hmm. The reason is, I mean, you can think of it. I don't. You can think of it. Why didn't I write the reason? Single tape, multi tape. So multi-tape means instead of one tape, now you'll have multiple tapes. So that's why your transition function changed. If you have k number of tapes, this is how it's going to look like. So you'll have to read k different characters from k of your tapes, uh, and then output also. You can change k different characters across k tapes, and then you have to decide the directions left or right for all the k tapes. So that's why you have power k. Now it's I think it's like that NFA and DFA thing. In NFA, you'll have multiple uh, branches, right? So if I'm talking about a multi-tape, I'll have multiple tapes. You can think about it. I think it's supposed to be simple. Non-deterministic Turing machine. Okay, how does a non-deterministic Turing machine look like? I mean, see, uh, in the deterministic version, whatever is there, for the output you put power set over done. So previously we had q cross tau cross l comma r, right? Now instead of that you'll have power set. Essentially, what is this telling? Instead of having one single unique output, now you can have a set of outputs. So how do you get that? You just use power set. You'll get it. So for let's say q, if you're in the current state q, let's say q1, and then you read on the tape the letter a. So q1 comma a, the possible outputs could be anything. It could be like q2 comma b comma left, q3 comma c comma right, q4 comma d comma left. So I gave you three different outputs. If I just put them in one place, it will become a set. So this is nothing but the power set of the power. This is nothing but the subset of the power set. So that is why this is the non-deterministic version of the Turing machine. You have three, not three, you can have multiple outputs. That is fine. A language recognized by Turing machine is Turing recognizable. Fine. Turing recognizable. Nice. Okay, now we have a different kind of Turing machine. A Turing machine that halts on every input symbol is a decider. Our usual Turing machine doesn't do that, right? It only halts when uh, when it enters the queue accept state or the queue reject state. But in this case, it's like on every input, it's going to halt. So that kind of a Turing machine is called a decider. And the language or the languages recognized by deciders are Turing decidable. So they have a name. So Turing recognizable, Turing decidable. So I think our usual Turing machines can now be called as recognizers. And this extra special Turing machine is a decider. So it halts on every input. It's a property of a decider. Any input can be represented using zero. Yes, I can convert literally anything into zeros and ones. So that is fine. And deterministic Turing machines and non-deterministic Turing machines are equivalent in terms of solving powers. They have the same powers. Now that we talk about this, I think you can recall what we've learned about P and NP, right? P is the class of, no, I mean, okay, fine. P is the set of all problems that are solvable in polynomial time using a deterministic Turing machine, right? And then NP is using non-deterministic Turing machine. But then here I say that deterministic and non-deterministic Turing machines, uh, both of them are equivalent in power. So why do we have P and NP? Are P is P and is NP the same thing? But then if you notice, I told uh, P is the set of all problems solvable in polynomial time. Solvable in polynomial time using deterministic Turing machines, and then NP is the set of all problems solvable in polynomial time, same time, polynomial time, but using non-deterministic Turing machines. If you remember, when I'm saying that deterministic Turing machine and non-deterministic Turing machines are equivalent, they're equivalent in solving the same set of problems, but here we are not considering the time. So if we consider the time, then things are going to change. And that's why we have two different sets of problems, P and NP. So problem is being solved in polynomial time. One using the deterministic Turing machine, the other is using the non-deterministic Turing machine. Uh, just because both of them solve the same set of problems, it doesn't mean they solve it in the same amount of time. For example, if we go back to DFAs and NFAs, I told you that both of them are equivalent. But I told you that uh, if if the NFA is solving its problems in such a way that it's sequentially like going through every possibility, like instead of simultaneously computing the solution, like I told that NFA is split into multiple branches, right? And if it's not doing that simultaneously, if it's doing that sequentially, like in a DFS or BFS manner, then that is exponential time. So in that case, we can say that DFAs solve problems faster than NFAs, but still they solve the same set of problems. But DFAs are faster. But NFAs will be equally fast if the computation happens sequentially across all, not sequentially, uh, parallelly across all branches simultaneously. So similarly, uh, okay, yes, you can go through it. So non-deterministic Turing machine, same story. So there you have states, right? Or maybe you can think of them as configurations too. Uh, so Turing machine, how can I represent a Turing machine? I can take a snapshot of Turing machine, right? So what will I get? Configuration. So every time my machine changes its state, my configuration changes. So I can represent the computation of a Turing machine as a series of change in configurations. So it's like you start with the starting configuration and then you keep changing configurations. That is essentially what a Turing machine does, right? So each configuration has this information, which is essentially the snapshot of the Turing machine. So it's like the Turing machine is like going through configurations. That is what I wrote here. So this is how a deterministic Turing machine looks like while it changes configurations. How does a non-deterministic Turing machine look like? It's like initially it will be there with a starting configuration. Then same story. It splits into multiple branches. So let's say this is C11, this is C12, C13, and then it goes on. So there are multiple possibilities. It just splits into multiple branches. So now the thing is, if the computation happens simultaneously, that is fine. The time complexity will depend on just the height of the tree. This is a tree, right? This is essentially a tree. If I and this is also a tree, but it's just linear. This is like a tree. It looks like a real tree. So uh, so if the computation happens simultaneously, then that is fine. The time complexity will be in the order of the height of this tree. But if the uh, computation doesn't happen simultaneously, if it happens sequentially in the sense, if if some BFS is applied or if some DFS is applied. Now, now before getting into BFS, what is going to happen if I apply DFS on this tree? So let's suppose DFS means you'll go like this, and keep going, right? The problem with applying DFS on this tree of configurations of a non-deterministic Turing machine is, I told you that there is a possibility where the Turing machine might not go into Q accept, might not go into Q reject, and it might just keep going in circles. So there is this possibility that this is going to enter a configuration, some CI, and then it's going to go to some other configuration, and then it's going to just go in loops. It will never reach the configuration where the state is going to be Q accept or Q reject. So in order to avoid such problems, we will not do DFS for Turing machine. We will simply do BFS. BFS will ensure that we won't loop into such uh, uh, into such problems. No, wait. BFS doing BFS will ensure that we won't go into a branch where such loop is happening. So okay, where was I anyways? Okay, we were doing BFS or DFS, right? So if the non-deterministic Turing machine is sequentially performing, so it's like first it will go here, then here, then here, then here, then here, then here, then here. So it will take exponential time. So this is not polynomial time. So it means uh, that problem, what is there? No, it will not fall in NP because even though it's being solved by a non-deterministic Turing machine, it is not being solved in polynomial time. So whatever is this problem, it will not come under NP. But this one, let's say this is let's say polynomial time. In polynomial time, it transitioned through each of these configurations. Uh, mm, so what does this mean? This is doing this in polynomial time. The problem is being solved in polynomial time using a deterministic Turing machine. So whatever is this problem, it will fall in the P class, the class of P. It will solve in class of P. If there is a non, or I mean, just because it's non-deterministic, it doesn't mean it can't have a polynomial time solution. For example, let's say this is the solution. Let's say that is the final configuration. So out of all these branches, if I just pick this branch, given that this is the solution, it means this is the accepting branch. And if this is done in polynomial time, it means uh, this this non-deterministic Turing machine has solved a problem in polynomial, assuming this is polynomial, has solved a problem in polynomial time. That would put this in which class? It would put this in the class of NP because it used a non-deterministic Turing machine to solve a problem in polynomial time. So when it's doing BFS, let's say the BFS took polynomial time. So that would mean it solved a given that this is the solution, it solved the non-deterministic Turing machine solved a problem in polynomial time, which would make this problem an element in the class of NP. So this n doesn't come from non-polynomial or something. NP is not non-polynomial or non-polynomial. N just comes from the non-deterministic version of the Turing machine. That's it. So, so recalling, what is class of P? Class of P is the set of all problems solvable in polynomial time using a deterministic Turing machine, and class of NP is the set of all problems solvable in uh, polynomial time using non-deterministic Turing machine. So the n in the NP comes from non-deterministic Turing machine. Uh, that is what I wrote here. Uh, okay, so this was the notes until last week. So last week I was not present, so I did not make any notes for that. Since I was absent, I asked Ravi Kishore sir to take a class for me, or I asked him if I could join online. He was like, "No, don't do that." He would take a class for me, so he did take a class for me. So now what I'll do is within the same folder, I will uh, tell you the topics that sir taught me, which is like after the Turing machine. So uh, the important part, it starts now, I think. So now from now on, I would like to assume that everyone understands what is a Turing machine, what is a decider, all the terminologies, Turing recognizable, what else? DFA, everyone should know what is DFA. Uh, Fine. So, and the fact that every input can be every input is basically zeros and ones. I can represent it using zeros and ones. I can represent machines as binary strings. I can. Okay, fine. So we'll just see. As in, when we go through the topics, we will see. Uh, how is this? Fine. Okay, before that, now, before we get into this one, last week, the last thing, last to last week, in the last to last week, the last thing that we discussed was something like this. How do we store input onto the tape? So in the starting, you have a tape, right? The tape is empty. The tape has blank characters. How do you store things onto the tape? This is your start state, right? Start. So this is the configuration of the Turing machine before you do anything. So as in when you give input, what you're supposed to do, just let's say your input is uh, let's say maybe S1, S2, S3. Let's say this is your input. So what you're supposed to do, just read the input, put it here, move your tape head, then do this, move. I mean your states also change, right? I mean I don't I I now that I think about it, do you even have to change your state? Do you even have to change your state? I don't think you have to change. It's up to you. So and then you move your tape head, you change this S3, and now if you want, you can just go back now. Now what just happened? You kept reading the input, but then you didn't perform any additional action or something of that sort. You just read the input, you just printed it on the tape, or you just pasted it on the tape, and then you just go back to the initial position. Now you can start reading your tape alphabet, and then I mean you can start reading from the tape, and we know that all input characters Si belongs to sigma, right? So we know that sigma is a subset of tau, because what does it mean? Every input character is also an element in the tape alphabet. So now I can start reading, I can start checking which state I am in currently, and then I can start reading my tape. So that would mean my elements are coming from tape alphabet. That is not a problem, because uh, if the tape has some input characters, I know that input characters, the set of input characters is a subset of tape alphabet. So there is no problem there. So I can consider S1. I can say that Si is an element of tau. There is no problem in that, because sigma is a subset of tau. That is not a problem. So what I just told here is how to store input onto a Turing machine. Just keep. So it's like, probably I think it looks like this. So you are in Q start, and then You want to read input, right? So how is the output going to look like? You be on the same state. You don't change your state. Maybe you could change your state, but there's no point, right? And then onto the tape, what do? You write SI, and then you just go right. So something like that. You keep doing this. Fine. So that is fine. I'll just that is fine. So fine. So the first thing that happened in the extra class that Sir took for me, which was supposed to be the topics that happened last week. So I'll be starting them now. How many hours has it been? 2:30, 3:30, 4:35. 3 hours. Okay, nice. TOC took 3 hours. I didn't expect to take 3 hours. Uh, but it's 5:30. I was like, I have to go at 5:30. So what I'll do now is stop for now. Yes, I'm stopping it for now. I have to go now. I'll continue this later. I'll just stop it early to start early tomorrow. So let me just stop this now.